In recent years, a large emphasis has been put on environmental preservation by organizations like the United States Environmental Protection Agency and the World Health Organization. One topic that has attracted significant attention is the treatment of wastewaters, especially within industry. While many forms of treatment exist, photofenton reactions, like the ones shown here, show tremendous upside as they can be adapted to treat many different types of contaminants. Their usage spans numerous different industries, including textiles, where they are commonly used to treat dye wastewater, agriculture, where they can be used to treat wastewater produced from sanitizing pesticide containers, and they can even be used in highly specialized industries like winemaking. So the Fenton reaction is classified as an advanced oxidation process, which are characterized by the formation of highly reactive hydroxyl radicals shown here. So the basic reaction involves the addition of hydrogen peroxide, H2O2, to iron 2 salts like iron 2 sulfate, which creates the hydroxyl radicals, OH minus and Fe3+, which, when adopting the appropriate pH of 2.7, allows for the reduction of Fe3+ back to Fe2+, which can be reused in the Fenton reaction. As we zoom in to focus on the photofenton reaction, we see a similar reaction to the original Fenton, with the addition of radiation, shown as H times nu. The radiation allows for increased production of hydroxyl radicals, as well as increased rates of degradation in the pretreatment of the pollutants. To maximize efficiency while minimizing cost, photofenton reactions are commonly used as a pretreatment step followed by traditional biological processing. This combined process can be done at lab or industrial scales, with only subtle differences existing between the two. The main difference is the way in which the photons are produced. At the smaller scale, the left diagram, UV lamps can be used. Because such lamps are not practical for the scaled-up process, compound parabolic collectors, or CPCs, like the one on the right, collect solar radiation for the reaction. One obvious limitation for the industrial-sized process is the need for the cheap solar energy to be collected. CPCs like the grouping shown here must be located in areas that get large amounts of sunlight, which could prevent more widespread use in the future. While there is an obvious difference in size between the laboratory and industrial bioreactors, both work almost the same. Prior to entering the biological system, the pH must be neutralized to around 7. Activated sludge from wastewater treatment plants is used as a base in the immobilized biomass reactors, where the biodegradation of the intermediates actually occurs. All in all, the photofenton and biological reactor system is one of the most viable options to help decontaminate industrial wastewaters. With degradation efficiency reaching as high as 89%, many industries should undoubtedly look to incorporate this technology into their production.
For this figure, the operational costs for 3 processes as a function of the percentage of TOC, that's total organic carbon removed. In the process that uses artificial UV light, which is represented by the red line and the blue line, 3 stages can be observed in the cost evolution. There's an initial decrease for low mineralization degrees, followed by a stable period, which is related to the most economically profitable conditions, and finally, a later period where costs increase sharply when TOC removal is higher than 75 to 80%. This finding is due to the low efficiency of hydrogen peroxide when sample molecules have been degraded. More reagents are needed to continue the mineralization process, and in contrast, the costs gradually decrease in the solar process. For higher rates of TOC removal, the solar process becomes cheaper. This figure shows that economically it doesn't make sense to eliminate 100% of the dissolved organic carbon with the photofenton process. The best method is to pre-treat the wastewater with photofenton and leave the residual organic content for the much cheaper biological treatment to degrade. Pre-treating wastewater this way enhances the biodegradability of the wastewater, and the residual organic content is necessary for the development of microorganisms. This is why the photofenton process is best when used in combination with biological treatment. This graph leads me to talk about the operating cost of the solar photofenton reaction process. As you can see, the pie graph is made up of reactants, energy, staff, maintenance, and additional costs. The main thing to notice is that reactants account for 65.5% of the costs, and energy costs are very, very low compared to other processes such as the artificial UV photofenton process. The reactants that are used in the process consist of iron and hydrogen peroxide.
It's important for the efficiency of the Fenton process that you have optimal concentrations of your reactants. Now these vary by the substance being degraded, but for phenolic compounds, the iron 3+ concentration is found to be best when it's around 0.5 millimoles per liter, and for the same reaction it is best when hydrogen peroxide is around 21.22 millimoles per liter as well. But if you're using ambi, the iron 3 concentration that is optimal is actually 0.3 millimoles per liter. Now if the concentration of hydrogen peroxide is larger than what you need, it will hinder the mineralization of the compound because hydrogen peroxide will compete with the pollutant to react with hydroxide radicals. Another important thing to consider when considering the efficiency of the process is the pH of the wastewater. It's important to stay around 3, and this is because as the pH rises, it lowers the oxidation potential of the hydroxide radical, and because iron will form FeH2O6 and react much more slowly with the hydrogen peroxide. However, if the pH is below 3, then the hydrogen peroxide stabilizes as H2O3+, while iron favors the formation of FeOH2+, and this would limit the hydroxide radicals needed to sustain the reaction. Another thing to consider when looking at the efficiency of the process is the reducing agent which you choose to use. For a classical Fenton process, we just use hydrogen peroxide, solar power, and iron 3+, but you could also choose to do an aerated Fenton process, which is oxygen, solar power, and iron 3+. However, it is found that using hydrogen peroxide is 2.5 times more effective than using oxygen. In the OVAR scale-up process, a large-scale industrial application of wastewater that contained 500 milligrams per liter of dissolved organic carbon was treated using a combined process of photofenton and biological, and this was used to treat the wastewater, and the resulting effluent contained only 80 milligrams per liter of dissolved organic carbon. In Switzerland, it costs $22 per meter cubed of wastewater to treat phenolic compounds, and then the effluent is sent to a biological reactor, which is lower in cost than $22 per meter cubed, and so at most the combined process would cost $44 per meter cubed. Similar processes in Switzerland to treat wastewater, mainly incineration and wet air oxidation, cost $200 per meter cubed. The main environmental concern about this process is the amount of dissolved iron left in the process effluent. The allowed maximum limits of iron in the water in Spain is 10 milligrams per liter and is 15 milligrams per liter in Brazil. From studies that have been conducted, a plant that treats phenolic contaminants was found to have an undetectable amount of iron in the effluent. A plant that produces cheese was found to have 1.9 milligrams per liter of iron in the effluent, and wastewater from a chemical laboratory was found to have 5.5 milligrams per liter of iron in the process effluent. All of these results are well below the maximum allowed limits, and therefore the environment will not become polluted or endangered. No studies reported harm to the environment at such low concentrations. Hydrogen peroxide also decomposes spontaneously on its own into water and oxygen and therefore would not pollute the environment. Sludge is produced as a byproduct of the Fenton process. Primarily, the sludge is in the form of iron oxyhydroxides. Approximately 40 to 180 milliliters of sludge is produced per liter of wastewater treated. Biological processes alone produce significantly more sludge, and 30 to 50% of the operating cost is spent on treating it. Sludge can be recycled back into the process, and this would reduce the amount of catalyst needed while decreasing the amount of dissolved iron in the effluent. A current area of research is the use of sludge as fuel in furnaces and boilers. If this is a viable option, it could reduce the cost of the process and be used as a cheaper alternative to oil, coal, or gas in industry.
Photophancin reactions are a good benefit to our ecosystems and other environments. As you can see, here's Paris in the 1900s. There's a hospital called Hotel Dior. They actually used to dump bodies, bandages, and basically any waste they had into the river that went straight through Paris. Therefore, a lot of the ecosystems and a lot of people suffered and became ill because of this fact. Nowadays, with photophancin reactions and a lot of care for our ecosystems and more of a human responsibility for the environment, we have a photophancin reaction and a river with live fish. I know these are very detailed diagrams, but as you can see, there's a big difference. Nowadays, we take very good care of our environment and what we do to prevent the ecosystems from being damaged. Photophancin reactions take waste products and make them more biodegradable so that way they don't harm our environment. Previous reactions like incineration and wet air oxidation would be more costly and take up more space, but photophancin reactions came along and these are a lot more cost efficient and a lot easier to do considering they involve only iron, hydrogen peroxide, and radiation, which can be from sunlight. So they can be produced anywhere basically in the world, but is more beneficial in areas with more sunlight. These processes help our environment be what it is today and try and reduce the human imprint that we all make.